Okay, so to pick up where we left off. Well, obviously, chemical compounds do form. We do get bonds forming. And if you remember in the last chapter, we talked a little bit about how unbonded atoms are a little bit like these wild, crazy tightrope walkers or rocks perched high on cliffs. They're pretty unstable, actually. They're not very stable. They have very high potential energy, and that makes them unstable. And when they bond, they end up at a lower energy level. So they end up at a place where they are more stable, and that energy ends up sort of contained in the chemical. You may have had, we're going to go into an extended metaphor here. You may have had a friend, or maybe it was you, who was just a little kind of wild, just bouncing off the walls, up for anything, up for adventure, just a free spirit. And if they partner with someone, sometimes they're a little bit less bouncing off the walls. There's a focus. They're a little bit calmer. Well, that's in essence what happens to atoms when they bond. The bond formation makes them more stable, and it makes them less sort of wild and unpredictable. There's a catch, though. It is a delicate balancing act. So, there's that person you've always thought was adorable. We'll call them Cutie Pie. And Cutie Pie is everything that's wonderful in this world. Cutie Pie is just awesome. Just smile thinking about Cutie Pie. Cutie Pie is fantastic. Cutie Pie is smart and sweet and charming, and you just like looking at Cutie Pie, and you'd be happy as anything if you could just sit under a tree and talk with Cutie Pie all day, or maybe read a book or sit on the couch and watch a movie and eat popcorn. I don't care. I just want to be next to Cutie Pie because Cutie Pie is awesome. There is a powerful force of attraction, clearly, between you and Cutie Pie. If you just shut up about Cutie Pie already, my goodness. So there's this powerful force of attraction. It pulls you towards Cutie Pie. You think about Cutie Pie. Longingly. You would just love to sit on a dock on a lake and dip your feet in the water next to Cutie Pie on a beautiful summer day. Nothing could be better. What could be better? My goodness. Spending time with Cutie Pie. There's a problem, however. So, Cutie Pie, sadly, has been best friends since, they were 3 with Best Friend. And Best Friend is a repulsive human being. Best Friend has, oozing pus-filled blisters covering their face. Best Friend is stupid. Best Friend is mean. Best Friend is horrible. There is nothing more repulsive in this world than Best Friend. You would rather have hot coals applied to your feet than spend an afternoon sitting around with Best Friend, because Best Friend is just that awful. Best Friend is she's repulsive. He's repulsive. I don't care. They're awful. They're a terrible person. And they're painful to look at, and they're painful to listen to, and they're not nice, and they're just awful. Ah! Jeez. They have slugs coming out of their ears. I don't know. What could be worse? Best Friend is like the worst thing in the universe. And your dear sweet Cutie Pie just loves Best Friend. I don't know what Cutie Pie sees in Best Friend, but they're nearly inseparable. You want to spend that lovely afternoon sitting under a tree, just chit-chatting with Cutie Pie about the world and the clouds and life? Guess who's coming along? Best Friend. Ugh! So it is a continual dance. It is a continual masterpiece of choreography to get as close as you possibly can to Cutie Pie while maintaining as much distance as you possibly can from Best Friend. Did I mention how terrible Best Friend is? Oh my God! Ah! I hate being really bad. They smell bad. I mean, they're just terrible. They got pus and slugs and smells. Who wants to be your best friend? No one, except Cutie Pie. It is a lot of work to find the appropriate location, you might imagine. How's this going to go over at homecoming? Dancing with Cutie Pie while attempting to maintain suitable distance from best friend. It's tough. Let me tell you, this is a challenge. This, my friends, this is what atoms go through every day. Can you appreciate their plight? Poor atoms. So, what's going on here is you've got that little positive nucleus. Let me get rid of some of this. I wasn't recording. At some point, these unstable high energy things are going to have to react to something. Well, one of their possibilities is forming a bond, and that is a reaction. And when they form that bond, they are at lower energy. Now, they're still balancing those attractive and repulsive forces. It's still a dance. Do you remember the metaphor or the visual we used, I guess, about solids and liquids and gases? And that if you take something that is a liquid and you transfer it into being a solid, this amount of energy is released out into the world. And if you take something that's a liquid and you convert it to being a gas, you have to put this amount of energy into it. That there's a difference in the amount of energy, and that energy is either absorbed by the material or it's released out into the world. Okay, well, note that there is a difference in energy between these things that are at high energy and very unstable before they bond, and at a lower, more stable energy level after they bond. Well, there are two things about covalent bonds. The first is the bond length. Okay, this is measured in picometers, and it's just the total distance between the nuclei of any two atoms. They don't have to be identical. This is any two atoms that are bonded. We have this bond length. This is the distance at which they find that attraction and repulsion balanced. Close enough to dance with Cutie Pie, you can't smell best friend. It all works out. So this is that middle ground they have found. Now, there is another characteristic of these bonds, and that's bond energy. So if you notice on this chart, you've got high energy unbonded things. So here's our carbon and our oxygen. Once they're bonded, they're much lower energy. Well, the difference in the amount of energy there, that's contained in the bond. So, I have a little trust exercise. Oh good, we have an even number. You will all need a partner. You will be receiving some rubber bands. Choose wisely. Bond energy and bond length. Those shorter bonds that took a lot more effort to pull back, and you said it would probably hurt a lot more if it snapped back on you, those actually contained a little bit more energy. So if you look at the chart listing bond lengths, and I think you can probably have just the top half of this memorized by tomorrow, right? I don't really expect you to memorize bond lengths. That would be stupid. You can look them up. So, but we can look at different elements that bond, and they're all going to have slightly different bond lengths. Well, depending on the length of the bond, there's going to be different energy contained in it. So carbon is a fabulous thing. Carbon loves to bond. Carbon bonds 4 times. It's got 4 sites for attachment. Basis of organic chemistry. Lucky us. Well, carbon is also well known for the fact that it forms single bonds with other carbon, it forms double bonds with other carbon, and wackily enough, it even forms triple bonds with other carbon. And the more bonds you have, guess what happens to the bond length? It gets shorter and shorter and shorter. Well, guess what happens to the amount of energy that's contained in that bond? It gets bigger and bigger and bigger. So, shorter bonds tend to have higher energy contained in them. And I am now going to tell you a story about my friend Mike. He's actually a friend of my husband's, Mike. He's an engineer. He's a smart guy. How many of you have heard of propane? All the hands go up. That's propane right there. 3 carbons linked up, bunch of hydrogens floating around it. That's all it is. Little 3 carbon chains, propane. Monkeys eat peanut butter. That's a mnemonic to remember the names of the carbon chain molecules. Methyl, ethyl, propyl. So, propane does something really nice when you light it on fire. It releases energy in the form of heat and light. We break these carbon bonds and we get energy out of it. How many of you got to school this morning by breaking carbon bonds? Or diesel, or kerosene, or natural gas, or if you have a paraffin-powered vehicle, you're burning a little candle that heats up the air, that spins a little paddle wheel that unwinds your rubber band on your vehicle. That's still breaking carbon bonds. So our whole culture right now, our whole society, our whole everything, economy, is built on breaking carbon bonds for energy. And propane is a really nice little carbon bond to break. 3 single carbon bonds. Fantastic. So back to Mike. Mike, being an engineer and a rather clever guy, as well as being a 13-year-old boy trapped in a 40-something-year-old engineer's body, built a really awesome potato gun. Dude! Because he was an engineer and a really smart guy, he had access to some pretty high-powered mathematics. So he built a propane-powered potato cannon. More energy than your old Axe body spray. Ha! No more Aquanet for Mike. Oh no. He did the calculations. He built this puppy. He had extra thick piping. He had, double adhesive on the joints. And you all understand the concept behind a potato cannon. We have typically a larger cylinder which gets filled with some sort of propellant. We stick a potato in the end of the darn thing. And we fill this cylinder with some sort of flammable substance, typically. We cap it, and then we light it off. And, of course, because Mike was an engineer and a really smart guy and really sophisticated, he had an actual ignition thing, no sticking a lighter in it. He had a push-button ignition sparker, and he had wired something up. And so you get a little spark in there, and what happens? The propane goes boom, and it expands rapidly. The expanding propane fills the cylinder, overflows the cylinder, and shoots said potato into space, and you have shreds of potato flying through the sky, and it is a thing of wonder and beauty, and all the 44/13-year-olds go and it's great. It's fantastic. It's lots of fun, right? This is a great way to blow up a bunch of potatoes. So, propane. 3 single carbon bonds. And Mike knows I tell this story. Mike showed up at a bonfire that friends of ours were having with his potato cannon, his propane-powered, well-engineered, calculated, planned out, well-constructed potato cannon, propane-powered potato cannon, and his bright, shiny, new red car. He was very, very, very particular about who got to park near him, and don't open your doors into me, and hey, don't lay that blanket on the hood of my car, you might scratch it, blah, 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 blah. And Mike said, you know what MAP gas is? No, I had never heard of MAP gas. Has anybody here ever heard of MAP gas? Okay. So MAP gas, I don't think you can buy it commercially anymore. MAP gas comes in little cylinders like propane. Oh. And what, several of the engineering type, real smart people at the bonfire said is like, oh, cool, MAP gas. Oh, great. Mike said, MAP gas, because I said, I don't know what MAP gas is. And he said, well, it gives you a little bit more oomph for your buck. You get more energy out of it. Oh, cool, excellent. I wonder what the structure of that is, because this is the way I think. I should look that up. I wonder what the chemical structure is. I bet there's a double bond in there. There must be. How else would you get more power out of it? So Mike had fired off the propane-powered potato cannon with his large flask of propane. He had a grill cylinder he was using to fill it. And great, fun, awesome, flying shreds of russets, raining over us like, manna from heaven of some sort. Awesome. And then he got out the MAP gas. Now, I had zipped down to the house to use the potty. I was ever so happy later that I had. What was reported by the people who were sitting up at the bonfire and Mike was firing, because he's a smart guy. He's an engineer. Come on, give him some credit. He wasn't firing it like around the bonfire with a bunch of people. That'd be stupid. He was out in the middle of the field, like where his car was parked. What the people at the bonfire reported hearing, they had been hearing all night was, poof, that familiar report of a potato being propelled at high velocity, high into the night sky, achieving heights no potato ever thought it would. So this they had been hearing, and then they heard, bang, crash, and then they heard silence. And they all called out from the bonfire, Mike? No answer. Mike? Nothing. Mike, seriously, you okay? Nothing. Now, it turned out Mike was not dead, which could have been the case, because there were very large shrapnel chunks of PVC pipe that could have easily severed his jugular in one fell swoop. He was not dead, he was just deaf. And he could not hear them calling his name because his entire very well-engineered potato cannon, specifically designed to handle the forces of combusting propane, which he, being a clever guy, had decided to put MAP gas in, had exploded into 1,000 shards. And it was not flying potato over the field in that last glorious moment. No, it was PVC pipe. Heavy-duty, thick-walled PVC pipe, because he bought the good stuff for his propane-powered potato cannon. So, when I got home, I, of course, looked up the molecular structure for MAP gas. Turns out, it's got a really big, fat triple bond in it. And then a little single bond. Multiple bonds tend to have much higher energy levels than single bonds. Now, I'm going to tell you this. By the time you get through chapters 9 and 11 in chemistry and chapter 4 in physics, I will put forth a challenge to you. God, I hope nobody ever takes this challenge. I keep saying it. Some year I'm going to get unlucky. By the time you get through 9 and 11 in chemistry and 4 in physics, you should have enough knowledge under your belt that you could actually do all the calculation for the forces that would be present in that their MAP gas-powered potato cannon. And you could, in theory, engineer your own MAP gas-powered potato cannon. I am not advising this. Though 6 months after the glorious shattering, oh, and by the way, Mike put 2 or 3 dents in his nice shiny new red car. Flying PVC shrapnel at high velocity, yeah, it'll do some damage. 6 months later, on a road trip with said very smart guy and a couple other friends, we were discussing this incident. I told him that I talk about it in my chemistry class. And he said, well, could we do the calculations for MAP gas? And I said, you know what, Mike, you could, and I can provide you with as much as you need. He's an electrical engineer, not a chemical engineer, not a mechanical engineer, not a civil engineer. An electrical engineer, pretty smart guy, didn't fully compute the forces contained in that there triple bond. So, do I expect you to memorize this table of bond lengths and bond energies? No, I do not. What I expect you to know is that when you look at a given chemical like oxygen bonding to itself, a single bond between 2 oxygens is going to be longer and lower energy. A double bond between 2 oxygens will be shorter and higher energy. Now, if we start going oxygen and carbon and hydrogen, all bets are off. There are too many variables. But if we're looking at carbon to carbon to carbon or oxygen to oxygen, those single bonds will always be longer. They will always be lower energy. Those double bonds will be shorter than single bonds. They will have more energy. Acetylene has double bonds. Wait, acetylene double or triple? I'd have to go back. No, acetylene's a triple bond. Acetylene gives you more energy per unit than propane does. That's why it's used in welding. We use oxyacetylene torches because it's got more energy. MAP gas is used not to blow up propane-powered potato cannons, but because if you're doing some plumbing and you're heating up pipes, it takes less time to heat that pipe up using MAP gas than it does using a propane torch, because you're getting more energy out for every bond you break. So you get more energy in the form of heat to do your work for you. Okay, tomorrow on your FIP, you will be predicting bond types. You will be ordering things in terms of length and energy, bonds, and you'll be describing differences between different types of bonds. There is some homework up on the board. Those are some questions that should help you get ready for stuff. Oh, and you'll also be predicting where areas of charge would be on polar molecules. So, FIP, and that's it.